Excellent. All right, sorry for the delay, everybody. Yeah, nice to meet you all. My name is Richard Feder. I'm a postdoc at Berkeley. I'm a member of SPHEREx and DESI, and today I'm very excited to tell you about SPHEREx and what we've been up to the past couple of months. A number of people from SPHEREx are not able to travel right now, so I'm happy to share some of their work, but also yeah, we hope that they can travel soon. So, okay, so what is SPHEREx? For those that aren't familiar, SPHEREx is a near-infrared telescope that's designed to take a full sky survey in roughly 100 near-infrared bands. And so as a small aperture telescope, SPHEREx is able to achieve this through a very large field of view. It's something like 40 square degrees. And this is a passively cooled telescope that is imaged onto two mosaics of H2RG arrays that look like this. So these are detectors similar to JWST. And what we add on top is this kind of novel filter called a linear variable filter. These have been used in planetary missions before, but this is the first time they're being used in cosmology. And what this allows us to do is to collect this multi-wavelength data. So for every roughly 6 arcsecond pixel on the sky, we're collecting a low-resolution near-infrared spectrum that spans 0.75 to 5 micron. And SPHEREx is organized around these three main science themes. Most of my experience is in the first two, and today I wanted to tell you about some of the cosmology we can do more generally, in addition to some discussion on inflation. So it's been a very exciting year. In March, we successfully launched from Vandenberg Space Force Base in California. This happened after 8 launch attempts, which I'm not going to comment on right now. But after the seventh one, a bunch of us decided to go skydiving, which was a terrible idea. But luckily, after some despair, we had a near perfect orbit injection, and we got these very beautiful photos of our observatory going into space. And following this period, we had about a month-and-a-half period called in-orbit checkout. So this is similar to commissioning. And during this period, some basic measurements of the instrument were taken, and something like 5 or 6 practice surveys were done. This was a very important period because there were actually some additional orbital observational constraints that came to light after data were taken, but this was all done very well. So to give you a sense of where SPHEREx lies in kind of wavelength magnitude space, I'm showing, I guess, in-flight derived sensitivity estimates for both the all-sky and the deep field surveys. So you can see that we're spanning this range that's overlapping at short wavelengths with optical I and Z band measurements, and on the far wavelength end with WISE broadband measurements. And so SPHEREx is relatively shallow compared to some of these surveys, though in the near infrared it's really pushing much deeper. Another thing to note with this is that when we quote the point source sensitivity, we're doing so per channel. And so, for example, if you wanted to co-add a number of channels in a certain range, for example, near WISE, we roughly approach the WISE depth from this data. And due to the orbit of SPHEREx, this sun-synchronous polar orbit, we have very deep coverage of the ecliptic poles. So I'm quoting something like 50, but this depends on your exact ecliptic coordinates. What this also means is that very early on we get very good coverage in the ecliptic poles, and so this is the beginning of some of our investigations right now. To give you a sense of this, here I just wanted to show you this is a DESI spectrum, and so these DESI spectra are excellent, and they've told us a lot. But once you add SPHEREx data, you really start to get a handle on what do these galaxies look like across this wavelength range. And so when I started looking at these, this is aperture photometry, so this is what we're using. But I was just really blown away. These look like the templates that we've been thinking about for years. Yeah, it's really gratifying to actually see this in practice. So, the thing that connects, SPHEREx to cosmology is through its redshift survey. So here I'm showing, I guess, a comparison of Roman and Euclid, and as well as SPHEREx to show the kind of range in terms of sky coverage and effective redshift depth. And so, we've used the simulations in order to, I guess, validate the resolving power that we have in terms of our spectral resolving power. And so in redshift forecasts that we've done, we found that we collect a really wide spectrum in terms of redshift quality. So, we're a magnitude limited survey, and so for bright sources, we forecast that we're able to collect many sub-percent type redshifts, and then this, as you go fainter, you start to really probe the more photometric type of photo-Zs, but in great number. And just to show you, what a sub-percent type redshift looks like, this is a simulated spectrum. Qualitatively, this is very different than what a standard like optical broadband type photo Z looks like. Often you're looking for a Balmer break or an emission line feature in other cases. Here, we're really getting a handle on the full spectrum. And so, you pick up features like the 1.6 micron bump, you pick up polycyclic aromatic hydrocarbons at longer wavelengths. And through these types of spectra, we can really achieve this type of redshift precision. And I also want to say that a lot of our forecasts are based off of standard template fitting approaches, but we've asked the question, can we do better? And I think the answer here is yes. So this is work that's been done in collaboration with Urosh and Liam Parker at UC Berkeley, where we've trained a probabilistic autoencoder model in order to do more reliable forward modeling of our SEDs. And so this helps with SED reconstruction and redshift estimation. And through this approach, it seems to work fairly well. It's robust to missing data. And when we compare against template fitting, we find that our PAE in blue is recovering on average more accurate redshifts, some with higher precision. And it bypasses some of the kind of brute force memory limitations that come with template fitting approaches. So what are we going to do with these redshifts? I know that most people in the room are familiar with inflation, but with all these sub-percent type redshifts, one can ask the question, can SPHEREx do BAO? And we're living in an era where DESI has really done trailblazing in terms of BAO measurements, and we've heard a lot of discussion this week about the types of tensions that come from this data and paths forward to doing this. So one direction I think is to push towards higher redshift. But what we've found from forecasts is that SPHEREx actually can fill a very unique gap in terms of low redshift BAO measurements. So here I'm showing some forecasts that I had done where, I guess these different colored lines are showing various SPHEREx tracers in terms of these sigma Z bins. And if you do an AP type forecast, you can find that for some of these low redshift bins, SPHEREx is actually providing really competitive constraints in terms of the isotropic BAO scale. And so this is largely due to the fact that SPHEREx is an all-sky survey, and there definitely is a dependence on redshift errors that needs to be modeled, and so this can be seen from the difference of the dashed lines from the solid. But I think that this should be a really interesting target to go for, and we're far above NP of 1, with these samples, so I think there's a lot of work to be done here. I think there's a lot of work to be done in terms of maybe BAO reconstruction for these, and especially when we're looking at such low redshifts where nonlinearities are stronger. But this is something that the team is thinking about. The topic that people are probably most familiar with, and we've heard about this week, is in terms of inflation. So this is one of the primary science objectives of SPHEREx. And for the power spectrum, our forecasts are largely driven by the lower accuracy redshifts that are residing at higher redshift. And our current forecast suggests that, assuming universality, that we can achieve a sigma FNL of around 0.8, and this is with the power spectrum alone. But as we all know, these types of measurements are quite hard, and if we're really going to push in terms of an order of magnitude, more precise than existing constraints from DESI and, B measurements, that we really need to have a good treatment of systematics, and we really need to face this head on. And so, I think that like there's a lot of information in the SPHEREx data that will help internally to try and characterize systematics, and hopefully that we can correct for some of these. Within the team, there's been a lot of work using the spherical Fourier-Bessel formula in order to both model certain types of effects, but also more recently to try and understand systematics mitigation. So if your systematic is low rank in your SFB space, then you can try to cut modes or try and identify modes that are problematic. And there's a whole bunch of literature from Henry Gebhardt and Robin Wen on this topic. And so I encourage you to read some of these papers. I will say that some of this machinery is being tested right now on BOSS in terms of a reanalysis, and they found some interesting things. So I think this will be an interesting avenue to pursue looking forward. Another thing I'll just say is that there's been a lot of work in the community on multi-tracer to improve constraints, and a lot of this I think is complicated by B-Phi, but there's been work suggesting that this can also help improve constraints. So I think this is a very interesting avenue. I think more work is needed to understand the interaction of these types of sample selections that are based off of observables and understand how they interact with systematics and our selection functions. But I'm also very curious, for people in the audience if they have thoughts on this. Okay, so in my last few minutes, I just wanted to highlight a couple of different applications that we are interested in with SPHEREx data. So we've heard a lot about CMB secondary anisotropies, and I think SPHEREx will really fill a nice role here. I think the way that I think about this is that people in the community have used WISE for many of these investigations or other photometric surveys, and so you can think of SPHEREx as providing a WISE-like sample, but with a lot of 10% redshift, let's say. And so, applications in CMB lensing and in KSC, I think these should be very, very interesting to see. The other one that I want to briefly highlight is that using these galaxy redshift surveys, I think we can learn a lot about the near-infrared intensity itself. And so, there's some study of CIB in terms of the far-infrared context, but SPHEREx is really capturing the near-infrared cosmic infrared background. And there's a lot of work to understand, what is the history of cosmic light production, what are the effects of nonlinearities on near-infrared observables. And what we find in our autospectrum analyses suggests that there's a lot of signal here, but to really tease this out, we need to use galaxy cross correlations in order to understand these signals. And you can see this nice plot. These are some plots from the mission paper, which should be out in a few weeks, I think. Search for some of these higher redshift lines, but these are very faint. But SPHEREx is really an intensity mapping machine, and so I think the rigor that's being placed in terms of image quality, I think will pay dividends in terms of all of the science, and hopefully we can hope to probe some of these higher redshift phenomena as well. Okay, so where are we? Our official survey started in May, on May 1st. A really nice way to visualize where we are is to just make full sky mosaics and look at these maps themselves. These full sky mosaics that I'm showing from Ari Sukerman and Julia Murgia are showing you a movie stepping through wavelength, what these maps look like on the sky. And I look at this and it's jaw dropping for me, after thinking about this data for so many years. We're finally here, we're mapping this data, we're doing it in 102 spectral channels. And don't mind the atmospheric blip that you saw there, but there's a lot of information in this data. There's clearly more to do with this data than the SPHEREx team can do alone. And so we really hope that the community will engage with this data. It's all public, and I'm happy to comment on this as well, but I think I'll wrap up here and just thank you for your attention. Right. Right. Yeah. So this is a good question. I think on the SPHEREx side, I think noise non-uniformity will be a large factor of variation. So this is driven by variations in the zodiacal light. But in principle, we should be able to characterize this fairly well. What you're alluding to, I think, is that for our initial targeting, we use reference catalogs from legacy survey, and so the concern is that these have systematics that we may inherit. I think that we're in a better situation than, for example, DESI ELGs, where you're really pushing on these broadband limits, like the kinds of pre-selections that we make in like Z band or R band are a bit shallower than this. But it is true that we need to understand dust extinction much better. I think we need to really understand star galaxy classification and separation in a robust manner. So I'm working with a student on this topic, but understanding these types of non-uniformity will be important. In terms of dust extinction, should SPHEREx may actually be able to help calibrate this itself. So there's been some interest in using these polycyclic aromatic hydrocarbons as like a complementary tracer to far infrared tracers of dust. And so in this limit, we have this over the full sky, like we don't have, DESI extinction maps over the full sky. And so I think this will be interesting work, but clearly there's a large laundry list of topics that need to be addressed, and where things ultimately land. I mean, I think that there will be a trade-off in terms of the magnitude of these systematics and the kinds of samples that we cut and how that translates. But it should be interesting. Mhm. There's no which. What do you mean by this? I'm sorry. Right, there's a sample variance type cancellation, or yeah, I may not be like super familiar with this topic, but um, right. Um, well, I mean, so the forecasts that we do are multi-tracer in the sense that we split in these sigma z bins, and this roughly tracks with the stellar mass, and so in this limit, we've done these, but uh, yeah, I don't know. I can maybe we can talk offline. I can point you to some things. Right. So are you asking per object case or both, or for the intensity mapping? Right. Yeah, I mean, I do know like they've already done cross correlations with like DESI, and you start to see some of these Balmer lines popping out. So in cross correlation, you can see these. In the auto, these are much, the lines are maybe 1% of the total intensity that you measure. So it's inherently going to be more challenging to tease these out. But I think that internally, like you can do cross correlations where we have this wide spectral range, and so you can take the cross spectrum of H alpha and passion alpha. You can use other shorter wavelength lines, like things like this. You can use features if you want, like PAH. I don't know. Yeah.